All right. So you need to know when to use these, and we talked about the power rule so far and the product rule. So power rule is when you just have like a monomial sitting there and you can just work with it. Product rule is if you have two functions multiplied together. And quotient rule is then if you have two functions divided, right? And there should be no surprise that you see subtraction in this problem because division and subtraction have gone hand in hand in various things. So here you see we have some function right here, f of x divided by some other function. Okay? And then it says here, now, in product rule, multiplication, like we said, is commutative with functions and things that we've had here so far. And so is addition, so we weren't too worried about it. Now we're dealing with division and subtraction, in which case order is very important. Makes a difference. So here, basically, I look at it as saying put g of x, which is really the bottom, just write it down, right? Times the derivative of the top, minus the top times the derivative of the bottom all over the bottom squared. Okay. But of course we see that g of x can't equal 0. Well, why is that? Can't divide by 0. All right, we're learning all sorts of things. So now let's say it was derivative of u over v. Wow, that's a really bad u. There we go. U over v. You think we could write it in a more simple form? What would it look like if we had to write quotient rule in this form? Just kind of follow where it's going. What would it be? U prime minus u v prime over v squared. Everybody good? Some people just like to see it that way because they're better with that. I will tell you later this year we will be doing lots with some substitutions with u's and v's, and so it might not be a bad idea to get caught up with them. This particular problem actually could be done two ways, and so I'll show you how it could be done two ways. It's because it has a monomial in the denominator. Whenever you see that, you have lots of options. Okay? And so let's actually just do this one quotient rule to start with, and then I'll show you maybe how you could have attempted a different way. So I would consider 3x squared plus 5 to be in the place of f of x, right? And x squared is in place of g of x. So here we go. We're going to take the derivative. I'll take the derivative of the left side. It's y prime. Got it. You got the other side. No? All right. So here we go. Derivative of the right, because obviously if you do it to one side, you got to do it to the other, right? You can't just pick and choose where you take the derivative. You got to do it to both sides. So we're going to take the derivative of the right side now, and so it says to take the bottom, which is x squared, and just write it down. Right? That would be the g of x portion that we just did. Maybe I'll erase this so we can kind of circle it as we go. So I just did the g of x part. Now I have to take that times f prime of x, which really means the derivative of the numerator, which happens to be what? 6x. And you got that by using the power rule, right? So that's why that was very helpful, because what's the derivative of the 5 that was up there? 0, right? Yeah, so we didn't have to do anything. All right, so now minus, okay? And then, yeah, we got the numerator. And I a lot of times even like to do brackets on this. I don't do it all the time. Whenever I subtract something, I know it's going to be a lot of stuff, I like to put brackets. So we've got f of x, which is the numerator. So 3x squared plus 5 times, so we did that part, times the derivative of the denominator, which is 2x. All over g of x, which is the bottom, so it's x squared, because that's what the bottom is, right? But I have to, in the rule, square it. Okay, how are we doing so far? Doing good? All right, well, let's clean this up a little bit. This first term here can just become 6x to the third minus, and I'm going to keep those brackets in there for now. I'm going to be careful. And basically, we have to distribute the 2x, right? So we're looking at 6x to the third, and then plus 10x. Do you agree that's our numerator so far? All over. Now, x squared squared means I took x squared times x squared, which is x to the 4th. Yep. Well, you add the exponents when it's like this. When it's a power to a power, you multiply. right? But we were lucky in this case because it was x squared squared. We could have done either one and gotten it right. So we're almost there. What's something very nice that happens but doesn't have to happen anymore? But yeah, we got 6x to the third and then minus 6x to the third, right? We're sitting right here. And now, so a lot of people see that and then they do this next step wrong. They know it's over x to the fourth. But what is over x to the fourth? A negative 10x. Very good. That negative's got to go through both of those. So it's negative 10x. But I think we can do better in this particular case. What was that? Yeah, take out an x on the numerator and denominator, right? So if I do that, I end up with negative 10 over x to the third is my derivative. Again, that general equation that'll let me find the slope of a point that was on the original at any x value that you tell me, as long as it was on the original. Okay, so you can't really ask me about 0, right? Because x being 0 is not part of the domain of this original function. Now, just imagine. Now, some of you are thinking, this is the shortcut. Just look back at that original function and imagine doing it by the definition, which is substitute in x plus delta x for all x's that you see, and then subtract the function and take the limit as delta x goes to 0, all that fun stuff we did before. That might take a while. Now, is everybody clear on doing it that way? Because this next way might make you slightly mad. I use something very handy. It's called algebra. This is really not working very well. Hey, all right, there we go. I can actually rewrite this original as we're so used to putting common denominators together that we fail to realize that if it has just a denominator like that, I can separate the numerator if I want. Right? You with me on that? Okay. If I wanted to, right? Now this works really handy if it's a monomial on the bottom, because this is then just 3 plus 5x to the negative 2 power. And so now if I take the derivative of 3 is 0, and then this is just power rule, which turns into, which is what we got.
What?
Now, is that always going to work? Well, no, it only works really nice if there's a monomial on the bottom. Okay? If otherwise, you have to go to quotient rule.
Oh, wait, no, that's the top.
Right.
That's not what it was.
Good? Everybody good with example 1? All right, moving on. So what we just did in that last problem, probably not going to work out as nice on this one. Okay? Because it's not a monomial on the bottom. But we can still use quotient rule. And just think back to using the definition on this one. That would be lots of fun. You do it and get back to me. I'll take the derivative of the left side. Got it. Okay. So now let's do the other side. Okay. So this numerator is your f of x, or your u if you like to do it that way. And the denominator is your v, or your g of x if you like to do it that way. So what should I write down first if we're going to follow the rules? 2 minus 3x, because you write down the bottom. Times? Why 4x minus 4? Derivative of the top. All right, now what? Minus? Again, bracket just for safety. Yeah, I'm sure. Parentheses. Okay, so what are you writing down now? 2x squared, the top, okay. Divided, or times, divide, what? Times, okay. Times negative 3, because that's the derivative of the bottom. All divided by the bottom squared. And in a little bit, I'm going to give you a little bit of helpful knowledge that will save you a lot of time. So we've got to take care of this little location right here and figure out what we got dealing on here. So we got an 8x minus 8. We're just distributing, that's all we're really doing. Minus 12x squared. Oh, almost dropped my pen there. Plus 12x, right? Minus, again, I do actually take it kind of slow when I do these because I do fear that negative in there just a little bit because it is very easy to make a mistake. And so now we got to distribute the negative 3. So what are we looking at here? Negative 3x squared plus 12x minus 9.
You got that wrong.
I do? Oh, okay, just checking. Thought I snuck that one by you, too. I thought I snuck that one by you, too.
He's trying to play it off like he didn't mean to do it.
Is the rest right? Now notice what I didn't do. I didn't take care of the bottom, did I? I strongly recommend you leave that there. Do not FOIL it out. Okay? For what we're going to use it for, and in some problems later, we're going to be able to factor stuff out and work with things, and it's easier to work with it in that form in the denominator than multiplied out. So that's going to make it be, at least you don't have to FOIL that stuff out, right? So whenever you get something like that in the denominator, just leave it. Okay? Oh, I ran out of, oh, there we go. A little bit too far. Okay, what do we got here? So we're going to leave our bottom as what do we got here? We got a negative 12x squared, and really this turns into a positive, right? 6x squared if I distribute the negative in there. So we've got positive 6x squared and negative 12x squared ends up with a result of negative 6x squared. So those are done. We got a 12x and an 8x. That's 20x so far, right? Now be careful. 20x so far, and then minus 12x, right? Or you could look at the 12x's canceling, right? So 8x. And we got a negative 8 over there and a negative 9 over here. But again, be careful. It's really positive, and so plus 1. Now, it's possible that the numerator factors, and if it does, good for the numerator. But for right now, this is a good form of the derivative. Yep. So our derivatives, have you noticed, as the functions get more complicated, the derivative is getting more complicated. Okay? Because these functions are changing direction a little bit more, so the derivative has to be able to change direction with it. Okay? If it goes from positive to negative slope, the derivative has to be able to do that. Okay? Any questions on quotient rule so far? Okay. Well, you might think the problems are really long, but again, we could do it by the definition if you'd prefer. I guarantee we'd still be working on some if we did. Okay, suppose we have u and v. They are some functions. Again, we know they are differentiable at x equals 1. But that's the only point. So maybe at x equals 2, it's not differentiable. What's that mean again, differentiable? You can find the derivative there. All right. So we know that function u, at 1, we get a point of 4. And at the derivative, if we put in 1, we get negative 2, so forth and so on. So determine the following derivatives. So I don't know what function u is. I don't know what function v is. But I do know I can take its derivative at 1. So let's take the derivative of u divided by v, some functions I've never seen. Well, it's v u prime minus u v prime all over v squared. And the point at which I am most concerned about is 1. It's the only point I know anything about. And I know actually quite a bit about it. But you notice this time I have thrown in some other information. Okay, v of 2 is 1, right? And that u prime of 3 is 3. Yeah, those probably aren't going to be very helpful, are they? Because I don't even know it's differentiable at 3. But here we go. V of, so point, the 1's the one I'm worried about. So we need v of 1 right here. That's what I need to figure out. Where is that? V of 1 is somewhere, and it's right here. So it's 2. times whatever u prime at 1 is. U prime at 1 is -2. Minus u at 1, that's right there, it's 4, times v prime at 1 is right here, which is 4, all over v at 1, whatever that happens to be squared. Where's v at 1? Is 2, right? Right there? 2. So now it turns into just a simple calculation that we could have handled probably a long time ago. So we've got order of operations, of course. Don't forget that the division bar is a grouping symbol, numerator and denominator separately. So we got what? -4 minus 16 all over 4, which is -20 over 4, otherwise known as, what does -5 represent? For what? So somebody said the derivative at 1, but for what? Yeah, for some function u divided by v. I don't even know what it is, but it's some function divided by another. And I know the slope at 1 of that mysterious function is -5. Okay? All right, why don't you try this one right now on your own, please? Again, if you're listening to the recording, actually, try it. Don't just wait for the answer. All right, let's see how you did. Should this answer just be reciprocal of the example 3a? No, because it's a completely different function. If you divide v over u, you're not just switching the numbers, you're switching the function itself. So you notice this is what the derivative would be, bottom derivative of the top, blah, blah, blah. And so it's u of 1, which is 4, times v prime at 1, which is 4, minus v of 1, which is 2, u prime at 1 is -2, right? U prime at 1 is -2, okay. All over u of 1 squared, and u of 1 is 4. Everybody good? So what do we got here? 16, actually plus 4, right? All over 16, so it's 20 over 16, otherwise known as 5/4. So again, that is the instantaneous rate of change or slope of the tangent line at function v over u at an x value of 1, y value 4. Okay. This last one, again, am I multiplying the functions by anything? No, so what's the derivative of function u? Well, it's u prime is the derivative of that because it's some function. Plus, yeah, it's just adding them together, so they're separate functions. So then we would just add the derivative of that, which is v prime. And so it's u prime at 1 is 4, plus v prime at 1, which is 4. Oh, okay. I almost really snuck that one by. U prime at 1 is -2, plus 4. I thought for sure I was going to sneak one of them by. Is 2. So once again, that would be some function I've never seen, u plus v. Maybe it combines nicely, maybe it doesn't. I don't know. I don't know what they look like. But I do know that if I add them together, the slope of the tangent line at 1 is 2.